So hello, in this presentation I will talk about a work that we've done here at the Imagine Institute to improve phenotyping from clinical reports using deep learning technology. It's a work that comes from the interest of the Institute into rare diseases, which are a set of diseases that gather around 6,000 to 7,000 diseases and concern around 300 million people worldwide. So it's a large set of diseases that concern a lot of people, but for every disease, there are not so much people that are concerned by it, and therefore it is difficult to handle. For example, it is estimated that 5 to 8 years are needed to have a proper diagnosis for children with a rare disease. So we need to improve the treatment of this disease and also gather as much information that we can as fast as we can. This is made easier by the fact that electronic health records are ubiquitous, but in these electronic health reports, there are also clinical reports which are free text, and they are a bit more difficult to handle. And it is estimated that around 80% of the phenotypic information is hidden only in text. So we need tools to deal with that. And one of these tools is Dr. House that does store information, help visualize it, and also analyze data and also natural language processing data. And this is what we want to do, and we want to improve on that. Though the way it deals with text data and more precisely the extraction of phenotypes as a representation of a patient is by matching clinical reports to a lexicon using a pattern and exact match. So it finds occurrences of terms that are contained in lexicon inside the clinical reports, and then in order to have some contextualization about these phenotypes, applies some segmentation and rules on top of it. So segmentation is about dividing the clinical reports into phrases and sentences. And then the rules are about saying, for example, if a sentence has a negation in it or concerns someone else than the patient. So it uses markers that it finds and that are markers of, for example, negation. For example, it's if you mention a phenotype with negation, what you do is saying that the phenotype is not present in the patient. So we want to distinguish the case in which the mention is about saying that the phenotype is present in the patient and the one where you say the patient doesn't have the phenotype. So what we want to do is to change this classical way of doing things in Dr. House with a way that involves deep learning technology to improve on the rules. So the first part stays the same. We still find matches of clinical terms that relate to phenotypes, but then we want to apply a deep learning model to give attributes to these terms that were found, to these mentions. And these attributes are in the number of 3. There is disambiguation attribute that says if the phenotype that was found, if the mention that was found is really a phenotype or not. For example, if you mention the flu, it can be to mention the disease or the vaccine. We also have a negation attribute to say if the phenotype is present or absent in the patient. And we have also a subject attribute to attribute the phenotype to the patient or its family. So in order to apply deep learning models, what we have to do first is to annotate some data. So what we do is use an expert that will annotate the terms that were found, the mention with the different attributes we want to predict, and then we feed the data that was annotated to an algorithm that will then produce a model. So first, we want to create the corpus. What we did is that we have at our disposal 2.5 million electronic health records, and we sample from that by provider, by service, ensuring that there was the same count of reports per provider to ensure diversity. And then we have not, we have only one report per patient. And then we do the annotation, and then this is our data set. So the annotation is based on what was found by matching, so this part doesn't change. We use the UMLS metathesaurus as a lexicon, so the Unified Medical Language System, and we use only the French portion of the metathesaurus since we are dealing with clinical reports that are written in French. Then from the lexicon, we take only 10 semantic subgroups that relate to phenotypes. On the terms that were in these subgroups, we do light normalization, which is accent removal and lower casing, and we do the same treatment to clinical reports, and then we align tokens in the clinical reports to the one of the lexicon, and we find the matches. Then we do the manual annotation, so with an expert that is provided with annotation guidelines that can be shorter or longer depending on task. And then it does the annotation on the Bright server. And we did evaluate the quality of the annotation doing redundant annotation by 2 experts on a subset of the data. So we have coherence kappa measures on these subsets. Once we have the data, this is the time to use our model. So our model is done in the following way. We first start a pipeline by doing tokenization. So we divide our clinical reports into token, roughly words, using Spacey library and the French model, a French model of this library. So for example, it divides the phrase Stevens-Johnson syndrome after influenza vaccine injection to Stevens-Johnson 1 token and syndrome another token, etc. Then the tokens are transformed into vectors by different embedding models, Fastex and Camembert, which make vectorial representation of the tokens. And then these representations are fed to our deep learning model, which is bi-directional recurrent neural network with cells that can be either gated recurrent units or long short-term memory units. And then at each step of the phrase, at each token, we do a prediction about the label of the token. So for example, here it's disambiguation, and Stevens-Johnson syndrome and influenza are 2 tokens on which we do the prediction, none of the other, because these 2 group of tokens were flagged as being phenotypes, potentially. And then the model tries to replicate the label that was given by the annotator that says, for example, that influenza here is not a phenotype because it's a vaccine, and Stevens-Johnson syndrome, however, is a phenotype. So the 2 embeddings that we use are Fastex and Camembert. They are a bit different. Fastex is a static embedding, so it does not matter where the token appears in the phrase or what is its surrounding. The vector representation of the token is always the same. While Camembert is contextualized embedding, so the vectorial representation does change. They were both pre-trained. So we took the pre-trained models, and then we further fine-tuned them on a set of 2.5 million clinical reports. There are some tricks regarding Camembert, which is limited to 512 tokens. So during training, we split randomly the reports to 512 tokens when they were exceeding that length. And also the tokenization is a bit different than one that's Spacey, and we use the FLAIR library to match the 2 tokenization process. And also during inference, the length limit was handled by FLAIR, which does splitting of the sentences and then does overlap the splitted representations. Once we have our model and once we have selected our model, we can test it. To do that, we used our data set, and we used a modified version of k-fold cross-validation, so in which we divide our data set into 2 parts. Here there are 5, but in reality there were 10. And one is set to be the test, and the 2 other ones are validation and train sets. So we add validation and train set to select the hyperparameters, and the test set is never seen during training. So the validation is here in order for us to select which hyperparameter does best once the model has been trained on the train set. And once we have selected the right model based on the validation set, we measure its final performance on the test set. We do that for all possible choice of the test set in our partition. And then we have an aggregate measure of how our system does. So the results, we have a data set of different annotated, we have different annotated data sets. Disambiguation and negation, this is the same set of clinical reports at the beginning that contains around 2,200 reports with various counts of tokens and terms. You can see that there are roughly about two tokens per term on average based on specific tokenization. So the subject dataset contains 1,000 reports roughly. So it was made separately because we needed some enrichment on the cases of terms that were related to family because it's a more rare occurrence. But the important thing here is that the kappa statistics are quite good. It's maybe a little less good for the disambiguation notation because it's a bit more tricky to apply, but still quite satisfactory. As for the performances of our model, so what you see here is a comparison of Dr. Warehouse classic version and Dr. Warehouse plus fast text embeddings and Dr. Warehouse plus Camembert embeddings, and in both last cases, deep learning model on top of that. So what you can see first, the first thing to note is that Dr. Warehouse Classic does not do disambiguation, so we compare our two algorithms to an algorithm that takes every mention to be a phenotype. And what we can see is that we do find that there are some error in this process, and that we can learn to distinguish between true mentions and false mentions. So it does quite well. So of course the F1 is better, but also we do not lose so much in terms of recall. Only 2 points. And in this occurrence, the fast text embedding does not do worse than the Camembert embedding, a little bit better actually, and so this is the one that we selected. In terms of negation, we do better on all accounts. And the Camembert is also better than the fast text embedding, and we gain around 10 points of F1, so it's quite good. And lastly, in terms of subject prediction, which is discriminating between patient and family mentions, we do quite better, roughly 40 points, roughly 30 points better than Dr. Rouse with expressions and rules. But we lose a little bit of recall, around 7 points. But given the importance of the gain that we have overall around the precision, we still feel that it's quite good. And here, the Camembert embedding really does better than the FastX one. So this was our results. And now about our future work, we plan to improve our model by replacing the first part of the pipeline, which is based on match, by a detection based on name entity recognition, and then we would need normalization in order to find back references in lexicons. We also plan to add some other attributes to our prediction system, namely hypothesis, and maybe other type of span, such as gene prediction and mutation as an attribute. We also are concerned by the fact that it is maybe problematic to say that report only belongs to one patient. For example, it can belong to a mother and a child, and we're working on that. And we also want to assess the transferability of our models across facilities, since we only trained from data from one facility. I would like to thank you for listening to me. Also thank the Imagine Institute and the Agence Nationale de la Recherche for funding this work. Thank you.